So I got this race car here, and I really want to know the physics behind this, specifically the motion of this vehicle. And so today we're going to talk about kinematics, which is the study of motion, and usually the first unit of AP Physics 1. And this video will briefly summarize this unit. So now we are going to when the car moves. So now the car itself has started to move. And now we got to calculate change of position. So we can first do this with distance, which is summing the total paths traveled, so summing them all together. So if we pretend these words represent 10 meters, the car goes here and here, it would be a total distance of 20 meters. But if we look at displacement, on the other hand, it's a straight line distance from the initial final positions, it would be 0 because we go here 10, then we go back to our initial position. So we only compare the initial and final positions in displacement. So now here we are with the three big terms in this unit, which is displacement, velocity, and acceleration. Displacement we define as just a change in position, or delta x, and it's denoted in meters, or a lowercase m. Velocity is the change in position over time, or delta x over delta t, which is meters per second. And acceleration is change in velocity over time, denoted as delta v over delta t, or we can call it meters per second, or more commonly meters per second squared. So what if you're given a problem where you have a graph? In this case, we have a position versus time graph. So in this case, you need to know that the y-axis in here is position, which is denoted usually as x, but keep in mind this is the y-axis. And then over here we have ourselves time on the x-axis, which as time gets this gets more further to the right, the time gets larger. And then here you can figure out the slope of this line, which will be velocity, as it is change in position over time. So that's velocity. And then, if applicable, if the curve is positive or a smiley face, the acceleration is positive. And if it's like a frowny face, the acceleration is negative. In this case, there's no curve, so there is zero acceleration. So now, in this case, what if you have velocity instead in the y direction instead of position? So then, now, here's what you do differently. So now, to find acceleration in this case, it's going to be the slope of this line, which is going to be delta v over delta t using our course for rise over run. And now, the area under the graph is delta x, which is the change in position or displacement. So, and going from time here to time there, the area under here would be the actual displacement. So now again, what if it is acceleration now in this direction? And so instead, to calculate velocity from here, you just need to look for the area under the graph. And the slope in this case will be, of course, delta a over delta t, which is change acceleration over time, which is jerk, which we will not cover in AP Physics 1, but keep in mind that jerk is one of the derivatives of position, just as acceleration and velocity are. So next we have our four kinematic equations, or you can call them UAMs. This is for uniform accelerated motion, which in this case, all these equations you can use here are applicable only if acceleration is constant, as in this unit, acceleration is always usually constant. And so here are the equations. Of course, d equals v initial times time plus 1/2 at squared. Here's the timeless equation, where if you need to solve for a final velocity and you don't know time, here's what I like to call the time full equation, is if you have the time and acceleration and need to find, of course, your final velocity. And this equation here is d equals v initial plus v final over 2 times t. That's for, of course, d, and that is not on your equation sheet. And so it's a good thing to memorize, and just keep in mind these work only if acceleration is constant. So you often see this cliff problem in this unit, where something is thrown off a cliff. So this happens to be a freefall problem because it's when an object is subject only to Earth's acceleration due to gravity, and acceleration is usually negative 9.8 meters per second squared, and the object will always have a constant negative 9.8 meters per second squared, while the speed will change. And usually if it's a projectile that is from horizontal like this, it often has 0 speed at the top, but still it has that constant negative 9.8 meters per second squared. So now we have advanced into 2G projectiles. So now this is where there are two directions where a projectile is fired from initial position. So here we have our initial of velocity vector called r for some reason. Usually it's called v or something. So yeah, so it comes out at r, and then it would come out at this angle somewhere down here that is supposedly theta, or whatever they mark it. So in order to find the components, we can use SOHCAHTOA. Often in this direction, this is sine, which is for y, because this is opposite over hypotenuse. And the angle is here. Then for the x component, it is usually cosine, which is the adjacent side, which is here, over the hypotenuse, of course. So you use the four kinematic formulas, or the UAMs. You can apply these. And also need to remember that gravity only affects the y component of velocity, while the x component is constant, which means there's no external forces in the x direction. However, gravity only affects the y, which means there will be a point where the y component will be 0, while, as always, x will be constant.